Indeterminate forms and L'Hopital's rule. Determinate and indeterminate forms. Let's consider the following statement about limits. If the limit as x approaches a of f of x equals c, and the limit as x approaches a of g of x is either plus or minus infinity, then the limit as x approaches a of the quotient f of x divided by g of x is equal to 0. One way that we can make the same statement in a condensed manner is to say that c divided by infinity equals 0. This is just shorthand for the previous statement about limits. And because of this, we can say that c divided by infinity is a determinate form because it always equals 0 no matter what the particular functions are involved. Now consider another statement about limits. If the limit as x approaches a of f of x and the limit as x approaches a of g of x are both 0, then the limit as x approaches a of the quotient f of x divided by g of x might equal any number or even fail to exist. A condensed or shorthand version of this statement is that the form 0 divided by 0 is indeterminate. That is, the limit of any quotient for which the numerator and denominator both approach 0 depends entirely upon the specific functions involved. Indeterminate forms. The most basic indeterminate form is 0 divided by 0. It is indeterminate because if the limit as x approaches a of f of x and the limit as x approaches a of g of x are both 0, then the limit as x approaches a of the quotient f of x divided by g of x might equal any number or even fail to exist. A couple of simple specific cases are the limit as x approaches 0 of sine x divided by x, which recall equals 1, and the limit as x approaches infinity of e to the minus x divided by sine of 1 over x. The forms infinity divided by infinity and 0 times infinity are also indeterminate. These are actually equivalent to 0 over 0, since any specific case of one can be recast as a specific case of another. For example, consider the limit as x approaches 0 from the right of x times log x. As it's written, this is a 0 times infinity limit, actually 0 times negative infinity. By rewriting x as 1 over x, we can rewrite this as the limit as x approaches 0 from the right of the natural log of x divided by 1 over x. Now the numerator and denominator here both approach infinity, and so this is an infinity divided by infinity limit. On the other hand, we could rewrite log x as 1 over log x, and write our limit as the limit of x divided by 1 over log x, in which case it becomes a 0 divided by 0 limit, or 0 divided by 0 indeterminate form. L'Hopital's rule. L'Hopital's rule is a theorem that helps us calculate indeterminate forms. Suppose that the limit as x approaches some number, or plus or minus infinity, of f of x divided by g of x is a 0 over 0 or infinity over infinity indeterminate form. Then, the limit of f of x divided by g of x is equal to the limit of the quotient of the derivatives f prime divided by g prime, provided, of course, this limit exists. Now let's look at an example of how we use this. Let's compute the limit as x approaches 1 of the square root of x minus the cube root of x, all divided by x minus 1. First, we check the numerator and denominator to determine what kind of form we have. As x approaches 1, clearly the numerator and the denominator both approach 0. So this is a 0 divided by 0 form. So L'Hopital's rule tells us we can take the limit of the quotient of the derivatives. Let's first take the derivative of the numerator. The derivative of x to the 1/2 power is going to be x to the minus 1/2 divided by 2. Now we subtract the derivative of x to the 1/3 power, which gives us minus x to the minus 2/3, all divided by 3. And the derivative of the denominator is just 1. So now we have a form that's no longer indeterminate. Clearly, as x approaches 1, the numerator approaches 1/2 minus 1/3, and so we have 1/6. That's our limit. Another example. Let's take the limit as x goes to 0 of x minus sine x divided by x times sine x. Here again, we clearly have a 0 divided by 0 form. So let's take the limit of the derivative of the numerator divided by the derivative of the denominator. The derivative of the numerator is 1 minus cosine x. We take the derivative of the denominator using the product rule. We'll have 1 times sine x plus x times cosine x. And now we notice that we still have a 0 divided by 0 form. So we can apply L'Hopital's rule again to this limit by again differentiating the numerator and denominator. The derivative of the numerator is just sine x. The derivative of the denominator is going to be cosine x plus 1 times cosine x plus x times the derivative of cosine x, or minus x sine x. Now we have a numerator that approaches 0, but a denominator that approaches 2. So this limit is 0 divided by 2, or 0. A few more examples. Let's take the limit as x approaches pi over 4 of tangent cubed x minus 1 divided by sine x minus cosine x. Since tangent of pi over 4 is 1, and since sine of pi over 4 and cosine of pi over 4 are both square root of 2 over 2, this is in fact a 0 divided by 0 form. So let's apply L'Hopital's rule. We'll take the derivative of the numerator using the chain rule to get 3 times tangent squared x times the derivative of tangent x, or secant squared x, and take the derivative of the denominator, getting cosine x plus sine x. So now notice that the denominator no longer approaches 0. Again, tangent of pi over 4 is 1. Secant of pi over 4 is 1 over cosine of pi over 4. So that's 2 divided by root 2. And when you square that, you get 4 divided by 2, or 2. So our numerator is 3 times 1 times 2. And the denominator is root 2 over 2 plus root 2 over 2, which is root 2. Now 2 over root 2 equals root 2, so this equals 3 times the square root of 2. Another example. The limit as x goes to infinity of the natural log of 3 to the x plus 2 to the x, all divided by x. As x goes to infinity, 3 to the x plus 2 to the x obviously goes to infinity, and so the log of that also goes to infinity. And since the denominator also goes to infinity, this is an infinity divided by infinity form, to which we can also apply L'Hopital's rule. Now notice that the derivative of the denominator is going to be 1, so we're just going to have the limit as x goes to infinity of the derivative of the natural log of 3 to the x plus 2 to the x, which is 1 over 3 to the x plus 2 to the x, times the derivative of 3 to the x plus 2 to the x. Now recall that we differentiate 3 to the x and 2 to the x in more or less the same way that we differentiate e to the x, except that we pick up factors of natural log 3 and natural log 2. In other words, the derivative is going to be 3 to the x times natural log of 3 plus 2 to the x times natural log of 2. Now this is still an infinity over infinity limit, but we can handle this in a simpler way than using L'Hopital's rule. Let's simply divide the numerator and denominator by 3 to the x. That gives us the limit as x goes to infinity of log 3 plus 2/3 to the x, log 2, divided by 1 plus 2/3 to the x. Now we know that since 2/3 is between 0 and 1, 2/3 to the x approaches 0 as x goes to infinity. So we have natural log of 3 plus 0 over 1 plus 0, or the natural log of 3. Another example. Let's take the limit as x goes to 0 of x minus sine x divided by x cubed. Let's first notice that the numerator and denominator both approach 0. So let's apply L'Hopital's rule. This is the limit as x goes to 0 of 1 minus cosine x divided by 3 times x squared. And now we still have a 0 divided by 0 form. So let's apply L'Hopital's rule again. We have the limit as x goes to 0 of sine x divided by 6x, and the numerator and denominator here still both approach 0. So let's apply L'Hopital's rule again. We get the limit as x goes to 0 of cosine x divided by 6, and so finally we have a denominator that doesn't approach 0, so this is no longer indeterminate. The value of the limit is 1/6. Limit properties of natural log of x and e to the x. We're now going to use L'Hopital's rule to compute some hopefully already familiar limits involving the natural log and exponential functions. The first of these is, if p is positive, then the limit as x approaches 0 from the right of x to the p times log x is 0. So let's approach the limit as x approaches 0 from the right of x to the p log x which is a 0 times infinity form using L'Hopital's rule. We first have to rewrite it as either a 0 divided by 0 or an infinity divided by infinity form. The most convenient approach here is to rewrite x to the p as 1 over x to the minus p, so that we have the limit of the natural log of x divided by x to the minus p, which has the form of infinity divided by infinity. Now let's apply L'Hopital's rule. We take the derivative of the numerator, getting 1 over x, and the derivative of the denominator, getting minus p times x to the minus p minus 1. Now the overall power of x here is negative 1 minus the quantity minus p minus 1, so that's minus 1 plus p plus 1, or p. So this quotient equals x to the pth power divided by minus p. And now clearly as x approaches 0, this approaches 0. Other important limits involving the natural log function: if p is greater than 0, then the limit as x goes to infinity of the natural log of x divided by x to the p is equal to 0, and the limit as x goes to infinity of x to the p divided by the natural log of x equals infinity. Now these are actually more or less equivalent. Anytime the limit of a positive function equals 0, the limit of its reciprocal will be infinity. So we only really need to derive one of these. Let's look at the limit as x goes to 0 of the natural log of x divided by x to the pth power, noting that this is an infinity divided by infinity form. So let's take the derivative of the numerator and the derivative of the denominator. We get 1 over x divided by p times x to the p minus 1. Now let's multiply the numerator and denominator by x, and we end up with the limit as x goes to infinity of 1 over p times x to the p, which is clearly 0. Now let's use L'Hopital's rule to show that if k is positive and n is an integer greater than or equal to 1, then the limit as x goes to infinity of x to the n times e to the minus kx is equal to 0, and the limit as x goes to infinity of e to the kx divided by x to the n is equal to infinity. So we really only need to prove one of them. So let's look at the limit as x goes to infinity of x to the n times e to the minus kx. Note that the first factor goes to infinity and the second factor approaches 0 as x goes to infinity, so we need to rewrite this either as an infinity over infinity form or a 0 divided by 0 form. The most natural thing to do here is to rewrite e to the minus kx as 1 over e to the kx, and now we have an infinity divided by infinity form. Now one application of L'Hopital's rule here gives us the limit as x goes to infinity of n times x to the n minus 1 divided by k times e to the kx. If k is greater than 1, this is still an infinity over infinity form. We'll apply L'Hopital's rule again, and we have n times n minus 1 times x to the n minus 2 over k squared e to the kx. And if n is bigger than 2, this is still an infinity over infinity form. This process can be continued until we get to x to the 0 power, at which time the numerator will look like n factorial, that is n times n minus 1 times n minus 2 and so forth down to 2 times 1, divided by k to the nth power times e to the kx. And once we arrive here, the denominator approaches infinity while the numerator is constant, and so we end up with a limit of 0. Exponential forms. Besides 0 divided by 0, infinity divided by infinity, and 0 times infinity, there are also 3 indeterminate exponential forms: 1 to the infinity power, 0 to the 0 power, and infinity to the 0 power. Now, because of the property of logarithms that says natural log of x to the p equals p times natural log of x, the natural log can be used to convert each of these exponential forms to 0 times infinity. The natural log of a 1 to the infinity form converts to an infinity times 0 form. The natural log of 0 to the 0 power converts to 0 times log of 0 being infinity, actually minus infinity, and log of infinity to the 0 becomes 0 times log of infinity, or 0 times infinity. So what all this means is that in order to compute an exponential indeterminate form, we can take the natural log of that form, find its limit, and then raise e to that power. In other words, if the limit of natural log of f of x is equal to L, then the limit of f of x equals e to the L. Let's look at an example. Let's find the limit as x goes to infinity of x to the 1 over x power. Now notice that the base x approaches infinity while the exponent approaches 0. So this is an infinity to the 0 power form. So let's first look instead at the natural log of x to the 1 over x power. The limit as x goes to infinity of the natural log of x to the 1 over x will be equal to the limit as x goes to infinity of 1 over x times natural log of x, which has the form of 0 times infinity. And by simply rewriting this as natural log of x divided by x, we have an infinity divided by infinity form. So let's apply L'Hopital's rule now. The derivative of the numerator is 1 over x, the derivative of the denominator is 1, and clearly the limit as x goes to infinity of 1 over x is equal to 0. So the limit of the log of our function equals 0, therefore the limit of the function itself must be e to the 0, which equals 1. Now let's look at a couple more examples of exponential indeterminate forms. Let's find the limit as x approaches 0 from the right of x to the x power. Now this is clearly a 0 to the 0 form, so let's look at the limit as x approaches 0 from the right of the natural log of x to the x. This equals the limit as x approaches 0 from the right of x times natural log of x. Now here let's just recall that this 0 times infinity form turns out to be 0 in this case. And so, since the limit of the natural log of x to the x is equal to 0, the limit of x to the x is equal to e to the 0, or 1. Another example. Let's find the limit as x approaches infinity of the x power of 1 plus a divided by x, where a is a constant. Now notice here that a divided by x approaches 0, so 1 plus that approaches 1, and so this is a 1 to the infinity form. So let's look at the limit as x goes to infinity of the natural log of that function. This equals the limit as x goes to infinity of x times the natural log of 1 plus a over x. So the first factor, x, approaches infinity. The second factor, the natural log of 1 plus a over x, approaches the log of 1, which is 0. So this is infinity times 0. Now we want to rewrite this as a 0 over 0 limit by putting 1 over x in the denominator. So now we apply L'Hopital's rule. We have now the limit as x goes to infinity of a quotient whose denominator is going to be minus 1 over x squared, and whose numerator is the derivative of the natural log of 1 plus a over x, which is 1 over 1 plus a over x, times the derivative of a over x, which is minus a over x squared. Now let's multiply the numerator and denominator here by x squared. Then minus a over x squared becomes minus a, minus 1 over x squared, and the denominator becomes minus 1, so that just gives us an a multiplying 1 over 1 plus a over x, and now we have a denominator that approaches 1, therefore this limit is equal to a. So the limit as x goes to infinity of the natural log of our function approaches a, therefore the limit as x goes to infinity of our function is equal to e to the a. Now we should remark here that this is very closely related to a common definition of e to the a. In fact, a common definition of the number e is this limit with a equal to 1. There's one more indeterminate form that we want to consider, and that's infinity minus infinity. Here's an example. Let's find the limit as x goes to infinity of the square root of x plus the square root of x minus the square root of x. So notice this is the difference of two terms that are both approaching infinity. Now the general approach for this type of problem is to try to combine the terms in some way in order to obtain a different kind of limit. Now we'll do this algebraically here. Let's take our function, and we're going to do a fairly common thing when one has the difference of square roots, and that is to multiply by the sum of those square roots divided by itself. So we're multiplying by the square root of x plus square root of x plus the square root of x divided by itself. Now when we multiply things out here, we'll have a numerator consisting only of the square of the first term minus the square of the second term. So the numerator is x plus the square root of x minus x. So now we'll simplify, and we have square root of x divided by the square root of x plus the square root of x plus the square root of x. Next, we'll divide the numerator and denominator by the square root of x. The numerator will then be 1, the second term in the denominator will then be 1, And when we multiply the first term in the denominator by 1 over the square root of x, the 1 over the square root of x goes underneath the radical as a 1 over x. And so we have 1 over the square root of 1 plus 1 over the square root of x plus 1. And so now clearly the limit as x goes to infinity of this function is equal to 1 over the square root of 1 plus 1, or 1/2. Another example. Let's find the limit as x goes to infinity of the natural log of x plus the natural log of x minus the natural log of x. Notice that as x goes to infinity, both terms are approaching infinity. Now, since we have the difference of natural logs here, we can combine terms by writing the log of the quotient. Now let's take the x plus log x divided by x and break that up into two terms. Now we know that as x goes to infinity, the natural log of x divided by x approaches 0. Therefore, this limit is equal to the natural log of 1, which is 0. Another example. The limit as x goes to infinity of e to the x plus e to the minus x minus e to the x. Again, we have the difference of two terms that both approach plus infinity. The first term here can be factored into e to the x times e to the minus x. So we can factor e to the x here. Now notice that we've got a product where the first factor approaches infinity and the second factor approaches e to the 0 minus 1, or 0. So let's rewrite e to the x as 1 over e to the minus x so that we have a 0 divided by 0 form. Now we can apply L'Hopital's rule. The derivative of the denominator is just minus e to the minus x, and the derivative of the numerator is going to be e to the minus x times the derivative of e to the minus x, which is minus e to the minus x. And so we have cancellation here, which tells us that this is the limit as x goes to infinity of e to the minus x. And as x goes to infinity, e to the minus x approaches 0, so this is going to approach e to the 0, which is 1.